Hi everyone, welcome to Math 251 Calculus 3. This is our first lecture, and in it we're going to do a couple of things. The main goal is to introduce a three-dimensional coordinate system because that's essentially going to be our playground for this entire course. Much like Calculus 1 and Calculus 2, we're focused on concepts related to the plane or 2 dimensions. In Calculus 3 it's all about 3 dimensions and higher. So that's our first goal, is to develop a three-dimensional coordinate system, some terminology and some tools to work in 3 dimensions. The second part of our goal in our first lecture is actually going to be the first thing that we encounter, and that is to just look at a couple of problems that we've seen before, and get a bit of a refresher. How did we deal with three-dimensional objects in our earlier calculus courses, for example? That's what this first problem is about. But also, how did we deal with other kinds of objects, so curves, implicit curves in 2 dimensions, and what kind of tools will we develop in this course that will help us solve problems more easily from previous classes. So that's our goal with these first 2 motivating problems, is to look back at objects we've dealt with in 3 dimensions before and see how we've dealt with them, what kind of tools we developed, with a little bit of a look ahead as to, hey, we're going to develop some new tools that will make solving these problems even simpler, and also to just really hit the ground running and start solving problems. That's really our main goal. So let's go ahead and look at this first problem. We wish to drill a hole in a sphere, removing points which lie within a circular cylinder whose axis goes through the center of the sphere. Okay, so we've got a sphere of radius 1, and our goal is to drill a hole right through the center of it. So we'll go north pole to south pole. And what I'll do is I'll just retrace these side portions, because then I will wipe out that part there. And so here's the hole we've just drilled out. And there is sort of our resulting sphere. So we sort of got something that looks like this. Maybe I'll draw another curve in there just so you can sort of get some perspective here. Okay, so there's the hole right through our sphere. We'd like to know, how big does this radius have to be? So we'll call this radius little r. How big does the radius of the hole have to be in order to carve out exactly half of the volume of the original sphere? So that means we should work out what the volume of a sphere with a hole of radius r is. So let's try to figure that out. Volume of sphere with the hole. How are we going to do that? Well, let's just look at the upper half. We'll look at the upper half. Why is that? Because with the upper half, I can now look at it as a solid of revolution by taking a curve. What curve am I interested in? Well, I'll draw that section of the curve. I'll highlight it in yellow. It's this curve right here, which is basically a portion of a circle of radius 1. So there's our portion of our circle of radius 1. So we're out here, value 1. We've chopped off or cut out a hole of radius r. So we're only looking at the portion of the circle of radius 1 between x equals r and x equals 1, if we're assuming this is the x-axis. And that's what we're revolving around this vertical axis. So now I'm thinking of it as a volume of a solid of revolution. That's where we dealt with 3-dimensional objects in Calculus 2, and we actually didn't need a 3-dimensional coordinate system to deal with that. We just worked with it by saying, hey, if we take a vertical slice and revolve just that vertical slice around, then what we get is a cylinder. And cylinders are familiar objects to us in terms of volumes and surface areas. And in this case, we are interested in the surface area. It's basically a label on a soup can, if you want to think about it that way. So we can always cut it open, unravel it. It's basically a rectangle. I know what the area of a rectangle is. So we dealt with objects in 3 dimensions just by manipulating them and pushing them down into 2 dimensions to get some of the basic formulas we needed. So the way we did this was we went, the volume of the upper half is equal to, here we did a shell method, so maybe I'll write up here, right above the equal sign, shell method. It's the integral from r to 1 of 2 pi times the radius of one of these shells. So the radius is given by this arbitrary x value. And then we've got the height of that particular part of the shell at the x value of x. Well, what is its height? Well, we have this curve. It lives on the curve, so it's x squared plus y squared is equal to 1. Or in other words, y for the upper portion is square root of 1 minus x squared. So that means that our height is the square root of 1 minus x squared dx. So remember, these things were radius and height. For the shell method, that's what we are integrating. 2 pi times the radius times the height of this arbitrary cylindrical shell, and then we integrate over all the shells that stack together and make up the solid. So in this particular case, we've got our 2 pi antiderivative of x square root of 1 minus x squared. So what is that? That would be 1 minus x squared. The antiderivative of a square root is a 3/2. And now I just think, if I was to differentiate this, do I get back to the 2 pi x square root of 1 minus x squared? Well, when I differentiate this, the 3/2 would come down. I don't want the 3/2 in front, so I'd have to put a 2/3 in front of here. In fact, I'll put a negative 1/3 in front of there and show you that that's enough. Because when I differentiate this, the 3/2 comes down, the 3's cancel, and I just have a negative half out front. But then with the chain rule, I get a 2x that comes out front, or negative 2x, sorry. And the negative 2 cancels with the negative 1/2 to just leave me with the x out front. So there's our antiderivative. That's going from r to 1. And so now we evaluate at the endpoints, and we get 2 pi by 3. The 1 goes in, gives a 0, and then we get minus. The r goes in, that gives us a 1 minus r squared to the 3/2. So that's the volume of just the upper half hemisphere with the hole removed. We want r such that the volume of the whole thing with the hole removed, which would be twice that we just computed, so 4 pi by 3, 1 minus r squared to the 3/2, is equal to half of the volume of a sphere of radius 1. So I'll write it like this: half of the volume of the sphere of radius 1. But we already know what the volume of a sphere of radius 1 is. That's 4/3 pi r cubed, but in this case r is 1, so 1 cubed is just 1. And so what we get is this equation. We're trying to solve for r such that this equation is true. Now I can cancel my 4/3 pi from each side, and what I get is 1 minus r squared to the 3/2 is equal to 1/2, or 1 minus r squared. Raise both sides to the power of 2/3. So power of 2/3 means you square and then cubed root. So this becomes a quarter, and then we are taking the cubed root of that, or the power of 1/3. And then we can go ahead and solve for r. So r squared is equal to 1 minus, maybe I'll write it this way, the cubed root of a quarter. And then we are square rooting that. So r is equal to the square root of 1 minus the cubed root of a quarter. And that's about 0.608. And so what that means is we've got our exact value of the radius, but we've also got an approximate value. And this says that if I start with a sphere of radius 1, then I'm going to have to drill a hole that's about 60% of the original radius, so 0.6, or more than halfway of across the original radius. I'm going to drill the hole, and that will remove exactly half of the volume of the sphere. All right, so the reason we did this one, again, this is again a look back, is because there was a couple of things here. One, we dealt with three-dimensional objects in Calculus 2 already, but we did them not really by fully embracing the three-dimensional coordinate system. We'll see later on in this course that we do this exact problem again, but there we embrace the fact that we're in a three-dimensional coordinate system and we use three-dimensional coordinates to deal with it. And we'll see that it's a little bit more straightforward to deal with. We don't have to, rely upon things like the shell method or the disk method to do this. We use instead this idea of a double or a triple integral, so integrals for higher dimensions. So that's really one of the reasons I wanted to introduce this problem. The other one is I just wanted to refresh your memory with some concepts from Calculus 2 and have them at our disposal so that we recall that we learned things like the shell method, and just refresh our memory with that so that we're able to use it again when we're required to do so in this course. All right, let's have a look at the next motivating problem. Here we've got a depth of a lake in the xy plane is given by this expression. So f of xy, so the depth at the point xy, is given by 32 minus x squared minus 4x minus 4y squared. So you may not have dealt with functions of two variables before. In this course we're going to be all about dealing with functions of two or more variables. But this might be for your first exposure to it, and that's fine. All this is saying is that we've got this lake, and if I'm thinking about the surface of the lake as just living in the xy plane, then I can pick various points on the surface. Those are given by a point in the plane, so x value and some y value. And given those x and y values, I can work out what the depth is of the lake right under that point. And that is what this expression gives me. F of x comma y, I just plug in x and y, and it gives me the depth at that particular point. What we'd like to do from this is sketch the shoreline. So this is in some sense about just interpreting what these questions are asking and then how to set them up mathematically. So what would the shoreline be? Well, you got to think, what is the depth at the shoreline of a lake? Well, the depth would be 0. When you're at the shoreline, there's no depth in the lake. The depth is 0. So here we've got that the shoreline is precisely where the depth is 0. But that's exactly what we mean by f of xy equal to 0. So what that has given us is now an equation. It's giving us an equation that characterizes the shoreline. So it's the set of all xy values, set of all points in the plane for which this equation is true. So now this is an implicitly defined function. The graph would be one of these implicit curves, or a curve in the plane, a set of all xy points that satisfy this. Let's just figure out what does that curve look like. So we're essentially back in Calculus 1 under the heading of implicit functions. So let's go ahead and just rearrange this a little bit. I'm going to move the x and y's to one side of the equation. I'm thinking of moving them over to the right, but then just reversing the left and right side of the equation. So in other words, I've got this stuff is equal to 32. Another way you can think about this is just move 32 over to the right and then negate both sides. However you do it, we get this equivalent equation for x and y's. From this, we can go ahead and complete the square. So I get an x plus 2 all squared plus 4y squared. When I completed the square, what I did was I actually added a 4 to the left-hand side of the equation because there's that 2 squared, that extra factor of a 2 squared that appears there. And so because that term appears on the left side, I've also got to add it to the right side. So there's a plus 4 on the right side as well. And now from this, we see that it's an ellipse. We can rearrange it just a little bit more. X plus 2 squared all over 36 plus y squared all over 9 is equal to 1. And that is an equation of an ellipse. What does it look like? Well, it looks something like this. So we're going to, actually I'm going to move this vertical axis over a little bit because the center is going to be at x equals -2 and y is going to be at 0. And then what else do we get? Well, I can think about, what are some of the points on this ellipse? Well, the easiest ones to find are the points where x is -2, sitting above this sort of center point. When x is -2, the equation becomes y squared over 9 equals 1, or y equals plus or minus 3. So we get 1, 2, 3, 1, 2, -3. So there's a couple of points on the ellipse. What about when y is equal to 0? Well, when y is equal to 0, I get x plus 2 squared is equal to 36. Or x plus 2 is plus or minus 6. So that means it's going to be 6 on either side of -2. So we get -1, 0, so that's plus 2, and then 3, 4, 5, 6. So out here at 4. And then I also get here, out here at -8. So -3, -4, -5, -6, -7, -8. So those are 4 points on the ellipse, and so then we can just connect them up to get the sketch of the ellipse. So there's our shoreline. It's an elliptical lake. The shoreline that looks like this. Now the idea is, for part 2, we're swimming at a point -1, 1 out in the lake. So at -1, 1, that's right about here. I'll put it in a different color, right about there. And the question is, which direction, so this is where Dr. J is swimming, which direction should Dr. J swim in order to stay at a constant depth? And also, what direction should he swim in order to increase his depth as rapidly as possible? So the idea is, when you're at a particular point, there is a corresponding curve that consists of the set of all points that have that same depth. Just like we did in part 1, we found the set of all points that have depth 0. We could, for part 2, find the set of all points that have depth equal to whatever the depth of -1, 1 is. Maybe we'll find that. So this is part 2. What is the depth at point -1, 1? Well, if we plug that in, -1, 1, we plug that into our expression up above, we get 32 minus 1, that's 31, and then we get a plus 4 and a minus 4, so we basically get a value of 31. So at that point, the depth is 31. And then we could say, okay, what is the set of all points that have depth 31? Set of all points at depth, or that have depth 31. What are they? Well, that would be the set of all points xy, where f of xy is equal to 31. Or in other words, 32 minus x squared minus 4x minus 4y squared is equal to 31. Or x squared plus 4x plus 4y squared is equal to 1. And then we can continue on. We could see it's an ellipse again. Maybe I'll complete the square one more time. X plus 2 all squared. So I've just added 4 to that side in order to complete the square, so I'll have to add 4 to the other side. This is an ellipse. It's the same center as it was before. So it's going to be an ellipse that looks something like this. Who knows where it goes around? We'd have to figure out where it actually hits the y-axis, and we could do that, but we're only interested in essentially what's going on right at the point 1, -1. So which direction would Dr. J have to swim in order to maintain a constant depth? Well, he should swim along a tangent line to the ellipse. You can see now this is where we can come back to questions or concepts from Calculus 1. Find the tangent line to an implicitly defined curve. How would he increase his depth as quickly as possible? Well, if going along a tangent line is going to maintain constant depth, then you should go in a direction that's perpendicular to that to increase your depth as quickly as possible. Because anytime you're swimming partly in a direction of the tangent line, then you're going to maintain a little bit of constant depth. So we want to go at a perpendicular direction. So we're really interested in, what's our tangent line and what's our normal to the curve at that point. Those are really the two questions we want. Maintain constant depth, tangent line. Increase depth as rapidly as possible, go at a normal direction or a perpendicular direction. And so we want to find a normal line. In this case, see the question asked about finding a unit vector that pointed in the direction. So how do we do that? Well, you can maybe start to think about how you would attack this problem in Calculus 1. I've got an implicitly defined curve. That's our constant depth curve. And I want to find the tangent to it. So we'd go ahead and we'd use implicit differentiation. I'm going to show you how we're going to develop tools in this course in order to attack this problem a little bit more straightforward. So this is our look ahead. This is how we're going to attack this problem in this course. We're going to look ahead. How are we going to do this? Well, I'd like to find a tangent vector. And I'd also like to find a normal vector. It turns out that of the two, when we're in Calculus 1, it's like tangent vectors. We're used to finding these are tangent lines. Think of these as tangent lines, but now that you've done linear algebra or are currently doing linear algebra and talking about vectors, we can also ask the question about a tangent vector because that's a direction as well as a magnitude. Turns out that the normal vector is given by the following. You take the derivative of our function with respect to x, treating y as a constant, and the derivative of our function with respect to y, where we treat x as a constant. And we'll say that in particular we're interested in the normal vector at -1, 1. So that means if I scroll all the way back up to the top and I see what is our function? Well, f sub x is just take its x derivative. Treat y as a constant, just like any other constant, even if you want to think of it as a c or just some number, that's fine. We're just going to think of this as a function of a single variable x, where y is some constant, take its derivative. So that becomes -2x minus 4. And then do the same thing with y. We're going to take its derivative with respect to y, that becomes -8y. And so we've got -2x minus 4, -8y. -2x minus 4, -8y. And so then, at -1, 1, this vector becomes -2 and -8. And since we're interested only in the unit vector, we can factor out a -2. For example, well, what we'll factor out is just the 2. And we are left with a -1 and a -4. And so then the unit vector that points in the same direction, I didn't want a reverse direction, that's why I kept the negative sign in the component. The unit vector, well, this is a vector of length root 17. So to normalize it, we divide by root 17. And we get, that's our unit vector. That's our unit vector that Dr. J would swim in order to swim in a direction that's perpendicular to the curve of constant depth. So that's going to take him in the direction where going into the deep end as fast as you can, that's the direction you want to swim in. How do we get the tangent vector in this case? Well, that would just be a vector that's perpendicular to the normal vector. And so this would be made up of f sub y and negative f sub x. And so in that case, we would have f sub y is negative 8y, negative f sub x is 2x plus 4, and then we'll get our unit vector, unit at negative 1, 1. I can just read it off from the other one, from below, by just switching the components and negating one of them. So we'll get a negative 4 and a 1. And so that is going to be our vector that's pointing in the direction of maintaining constant depth. So we've got our one vector that points in the direction of maintaining constant depth. We have our other vector that points in the direction where the depth increases as much as possible. So this was a look ahead, because we took this function of two variables and we looked at two kinds of derivatives, a derivative with respect to one variable and a derivative with respect to another variable. These are known as the partial derivatives, which we will get to in chapter 14. But I just wanted to show you that these ideas that we will be developing, we can come back and we can answer questions that we could certainly understand back in Calculus 1. This was a question really about implicitly defined functions and finding tangent lines and normal lines to them. But we can see now that we can do this using the concepts of partial derivatives, and we will develop these ideas in this course. So this problem is a little bit of a look back with a significant look ahead about how we will attack these kinds of problems. It's all right if you didn't understand the details of these. All I'm doing is just getting you thinking in the direction of, hey, what kind of problems are we going to be looking at in this course? These are some of the kinds of problems we will be looking at in this course. At any time in this course, when you're learning a new concept, I do want you to stop and think back to Calculus 1 and Calculus 2 and think, this new concept I just learned, can it help me solve problems I had in Calculus 1 and Calculus 2? And almost always the answer is going to be yes. The idea is we're developing new tools, and every time we develop a new tool, it'll likely be able to help us solve problems in the previous courses, where in the previous courses we learned special techniques to solve some problems, for example, like the shell method for finding a volume. In this course we are going to learn general methods of where that specific method we learned in, say, Calculus 2, the shell method, is just a small part of a much more general method we are learning in this course. So it's always good to stop, think back, what kind of problems did I learn in Calculus 1 and Calculus 2? Do the tools I'm learning in this course help me solve those ones? The answer should always be yes, but it's good to think about how and why. Alright, so that's it for the first part of this video. In the second part, we are going to get into three-dimensional coordinate systems, the terminology around them, and sketching some examples of graphs of equations in multiple variables. Alright, we'll see you in the next video.